Okay, so we'll begin. Are there questions?
Yeah, sir.
Yes, go ahead, please.
So is it possible that some sort of a coupling, let's say for in the electromagnetic case, we'll have charge as a coupling constant, right?
Yeah, roughly.
Yeah. So is it possible that the coupling here is some E, and with some other field, the coupling is E square or something?
Yeah, that's certainly possible. I mean, the same parameter may enter different terms in the Lagrangian in different ways. Right? But typically the point is every term has a separate independent coupling constant, right? Unless there is some symmetry which relates them.
Yeah. So I was thinking like, suppose I had some E times some field phi, or let it be lambda times some field phi 4.
Yeah.
And the same coupling constant lambda times phi 6 with some additional parameter to make the dimensions fine.
Okay.
And that parameter is not a perturbative parameter. Like, it's not a parameter of the theory. It's just something like c square or something.
Yeah.
So like this is one example, and another example where I have lambda times phi 4 and some lambda square times phi 6 or something.
Yeah. Okay.
So if I'm considering a perturbative analysis, then should I at the level of Lagrangian say that lambda square is smaller than lambda, so I need not consider them?
Not that you need not consider them. You can say that to leading order, you need not consider them. But suppose you want to calculate the lambda order lambda square term, right?
Yeah.
Then you can get the order lambda square term by using two interaction vortices each of order lambda, right? That's a lambda 5 to the 4. Or you can get order lambda square by using one interaction vortex, which is 5 to the 6, right? And both have to be included. If one is lambda, the other one is lambda square, then it's not that you can throw away the lambda square term altogether.
Okay. So if you recall the part where we were talking about in a phi 6 theory instead of phi 4 theory, to make it renormalizable, you said we have to add infinitely many terms to the Lagrangian itself.
Yes.
So with the parameters, are all the parameters different, or are they some lambda times
So in
m
general, they
function?
are all different, right? There is no
Okay.
principle which determines the relationship.
So there will be some lambda 1 coupling constant, some lambda 2, some lambda 3,
Yes,
and so on.
that's right.
And also this m, the mass of the field, that is a physical observable.
Not the m that enters the Lagrangian, but the physical mass.
Yeah. So I was thinking that there is some relation with m between m and mp, and there is a physical relation in the sense that we have an observable that determines the mass. So there must also be an observable that determines this coupling constant lambda or something, some function of lambda and m,
Yes,
another observable
that's right.
that we should be relating to a coupling constant term.
Yes.
So what is that in
That's the
the
4-point coupling, right? If you calculate the phi scattering, for example, right? Imagine that in the 5 to the 4 theory, you calculate the scattering of 4 phis.
scattering, like 2 going to 2 or something?
Yeah, say 2 going to 2.
Okay.
Right? Then that gets contribution from 4-point coupling, right? The
Yeah.
leading order diagram is the 4-point contact vortex, right? 1 point with 4 lines coming out.
Yeah.
Right? So the result of that experiment will be controlled by this parameter lambda.
I mean, okay, yeah.
Right? So that's what will determine this constant, the second coupling.
Yeah, but it is not unique in that sense. I could have very well said the 2 going to 4 particle thing also determines lambda.
Yeah, exactly. So the point is that then the consistency of all this is a non-trivial prediction of quantum field theory, right? That whether you use the 4-point coupling or 2 goes to 2 or 2 goes to 4 to determine lambda, you should get the same value. Right? That's
And
why
that is the condition for renormalizability.
exactly, yeah. Well, in a renormalizable theory, that automatically happens because there are only finite number of constants. Right? So once you determine, say, these two of the parameters, right? Say MP and lambda physical by doing 2 experiments. Then the rest of the experimental results are predictions of the quantum field theory.
Okay, yeah.
So whether you use 2 goes to 4 or 2 goes to 2 to determine lambda, that doesn't matter, right? Because the main point is the internal consistency of all these equations, right? Because you are eliminating 2 of them, and then everything else is determined automatically.
I was thinking of some sort of a uniqueness in the coupling of lambda, in the sense that, for instance, we have mass, which will also eventually couple to gravity.
Yes.
So that will be MP, right? The coupling there.
Yeah, it will be MP.
So in that sense, if I were to add some physical field to this theory, how will lambda couple to that?
Well, that is not a priori clear, right? I mean, the reason that the gravity couples to mass, there is a very specific reason, right? The general coordinate invariance. Not every physical quantity may have that interpretation, right? That there is something that couples to it.
I mean,
But
isn't
lambda
that
is
how
a physically
we
measurable
start?
quantity, right? Lambda is a physically measurable quantity.
Yeah.
And that's all it matters. You can measure it in many different ways, right? And if the theory is correct, then all these different ways should give the same value of that measured parameter.
Yeah, like, but in the case of mass, we only had like one consistent definition, like the pole of the 2 points function.
Yeah, see here you don't have that definition, right? You can make some arbitrary definition if you like, right? Like is the value of the square root of the scattering cross section when 2 particles come in, right? And go in 2 orthogonal directions of the 2 directions orthogonal to the original motion, right? You can choose that with the definition of that 4-point function of that parameter.
I see.
But that's just an artificial choice, right? Instead of saying they go out at right angle, you could have also said that they go out at 30-degree angle, right? And that's what you use to define your parameter.
Yeah, but then we won't be able to ascribe this lambda to the particle, in the sense that mass we are ascribing to an electron, even charge we are ascribing to an electron, spin we are, and so on and
Yeah,
so
so
forth.
lambda in a sense is never assigned to a particle anyway, because lambda typically couples different fields, right? Since
Yeah,
we
so
consider 5 to the 4th theory, of course, there is only one field, but typically a general interaction term will have many different fields involved. Right? So it's not a particular property of the particle, right? It's a property of how the particles interact with each other.
okay, and that is only encaptured in field theoretic models.
Well, I mean, you can say it's encaptured in the experiments, right? Scattering cross section is something that you can measure irrespective of whether quantum field theory describes underlying physics or not.
Yeah, but like so far I am not able to see the scattering element. I'm not able to compare it with what we usually calculate in quantum mechanics, the scattering element using Schrodinger's equation.
Yeah, but we relate it to the experiment, no?
Yeah, experimentally we'll get some results and we can compare it to that.
Yes.
But like we, for instance, we often say that quantum mechanics under some appropriate limit we can see classical uh, observables coming out, in the sense that mathematically.
Yeah.
So in that sense, can I under some limit or under some substitution see the scattering element or to come out to be the same as what we do in normal quantum mechanics,
Yeah.
relativistic or non-relativistic?
To do the same procedure in Schrodinger field theory, for example,
Yeah.
right? You will get the normal scattering that you are familiar with in quantum mechanics.
So how will I compare the 2-particle going to 4-particle thing then?
Oh, the 2-particle going to 4-particle doesn't exist in Schrodinger field theory. Normal quantum mechanics doesn't have that, right?
So taking some limit in that case would what give me zeros?
Yeah. So it's the point is, okay, you are comparing quantum mechanics with quantum mechanics, right? Not with classical physics.
Yeah.
You are thinking of the single particle quantum mechanics versus quantum field theory. And if you have processes where you have particle production, then that is not describable in single particle quantum mechanics. Right? So it's not, I think, the question of taking the classical limit that you're talking about. It's really how to get quantum mechanics out of quantum field theory. And that's possible as long as there is a particle production.
Yeah.
Right? If you are working at energies that is below the threshold for producing, say, 2 particle going to 4 particle, that 2 particle going to 4 particle means that in the center of mass frame, the total energy of the 2 particles must be larger than 4 times the mass of the particle, right?
Yeah. So can we sort of say that this is like unique character of quantum field theory? This a process like 2 particles going to 4 particles.
Well, we can say that quantum field theory is a tool that is well suited for describing this process. Right? There may be other formulations of quantum theory which also has this feature.
Okay.
Right? But quantum field theory is a convenient tool to describe this.
All right. And lastly, can we compare the 2 going to 4 amplitude with the 2 going to 2 amplitude? In the sense that in experiment, I want to know the relative probability of how often a 4 particles are produced with respect to 2 particles overall.
Yeah, you can
Will that come out to be 0 or?
No, it will not come out to be 0, right? I mean, we have the formula, right? We derive the formula for the S matrix, and then you also saw how to relate the S matrix to actual probability. So you can calculate the 2 goes to 2, right? Integrate over the final state momenta, say, right? There are the 2 final state particles, so you have to integrate over their momenta. That gives the total probability for 2 goes to 2. Similarly, for 2 goes to 4, you integrate over the probabilities over the momenta of the 4 final state particles. Both are numbers, right, that you can get out of quantum field theory, and then you can calculate the ratio and see, for example, if 2 goes to 4 is more dominant or 2 goes to 2 is more dominant.
Yeah, I was thinking that, by some weird intuition that it should be 0.
No, it's not 0 actually. I mean, at low energy, you expect that 2 goes to 4 is suppressed, right? I mean, it may not even be possible, right? Then the 2 goes to 2 obviously dominates over 2 goes to 4. But if you look at it very high energy, right, then typically particles tend to produce large number of outgoing particles. So then the 2 goes to 2 will be a very small fraction of the total probability.
But can I for sure say that 2 going to 2 is more probable than 2 going to 4 always? No.
No, not necessarily.
Okay.
Yeah, it's in perturbation theory, we can say that it may be more probable because 2 goes to 4 may involve more couplings, more parts of the
lambda to the 4 or something.
Exactly, right? So from that perspective, you can say, yes, that is true. Right? In perturbation theory, 2 goes to 4 is less likely. But in general, no. There is no general principle of quantum field theory which tells us that 2 goes to 4 is less likely compared to 2 goes to 2.
All right. Also, one more thing. Could you, in the next, if possible, in the next problem set or something, as an optional problem, maybe give some example of a Hamiltonian where on quantizing we may see the anomalous symmetry breaking, some symmetry being anomalous?
See, anomaly, you cannot, I mean, I can set up the problem, but with the technology that we have learned so far, I think it will be difficult to do because it requires loops, right? And anomalies are closely tied to ultraviolet divergences in the loops. Right? So unless you know how to deal with ultraviolet divergences, I think you will not be able to see anomalies, right? In quantum field theory too, right? I think anomalies probably I will not be taught in quantum field theory too, but at least there, after you have learned how to tackle ultraviolet divergence, you can then solve a problem of this kind, right? Because I don't think in this course, I mean, whatever you have learned so far, right, you will be able to see this.
Okay.
Because it will really introducing ultraviolet regulators, right? And it's basically you will find that there is no possible ultraviolet regulator that maintains a particular symmetry that you're talking
about. Okay.
So I think for that you have to really wait till next semester.
All right.
Any other question? Okay, so if not, let me begin. So what we learned last time is that if we have classical Maxwell's theory, okay, then we can describe it in terms of the Rauthian, where we treat the field A0, the zeroth component of the vector potential, in the Lagrangian formulation, whereas all the spatial components A1, A2, and A3 in the Hamiltonian formulation. And then we saw that in the Coulomb gauge, the Rauthian takes a very specific form, okay, where the A0 basically disappears because A0 is set equal to 0 by the equations of motion in the Coulomb gauge. And the Rauthian has this simple form. It has the square of the momentum that is conjugate to the AIs. And then you have some kind of term involving the AIs. Okay? But we have written in terms of the magnetic field, DI. DI is determined in terms of the AIs in this form, by this equation, or equivalently by saying that D is curl of A. And because we have eliminated the A0 variable, right, now the Rauthian essentially acts like a Hamiltonian. Okay? Because as far as the pi i's and AIs are concerned, the Rauthian is like a Hamiltonian. So then the equations of motion derived from the Rauthian takes the standard form of Hamilton's equation, namely del AI del T is equal to the derivative, functional derivative of R with respect to pi I, which in this case happens to be pi I itself. And del pi I del T is minus the functional derivative of R with respect to AI. And with some little work, one can show that this is given by curl of B, okay, or minus curl of B. Okay, so to do this, you have to write B in terms of A, okay, then calculate the variation, okay, and then rewrite this in terms of B. And finally, we also have to remember that you have additional constraints, okay, in this formalism. Okay. This one comes from the Coulomb gauge fixing condition, and this one came from the A0 equation. Okay. But now that you have forgotten about A0, we'll just regard this as some external constraints that you have imposed on the coordinates and the momenta. And one of the important observations here is that these constraints are preserved by equations of motion, which basically means that once you impose them at t equal to t0, they remain valid at all times. And so let me quickly go through it again, how we prove this. To prove that this constant is preserved by the equations of motion, we calculate the time derivative of this constant. So the del t you can bring to the right of the spatial derivative. And then we use this equation to write this as del I pi I. And that, of course, is 0 by the second constant. Similarly, if you take the time derivative of this, that becomes del I of del t pi I. Again, you use equation of motion. This is curl of B. So essentially what you get is minus divergence of curl of B. And that, of course, is 0, because divergence of curl is always 0. Okay? In this index notation, you see that this becomes del I of epsilon ijk del j bk. Okay? And because of the antisymmetry in I and j, this term just vanishes. Okay, so this is what we had achieved last time. Are there questions on this?
So,
yes, go ahead, please.
If we put the gauge condition that the divergence of A is 0, and we use the equations of motion to find that A0 is trivially 0 always. But
yes.
I mean, at the level of Rauthian, we shouldn't do that, right? I mean, we should not use the equations of motion to find the constraints.
Okay, so the point is that we are trying to find a system whose dynamical equations are the same as the original equations. Right?
Yeah.
We know what the original equations are. So from the Rauthian, we have these two equations. Right? From this Rauthian.
Yeah.
Okay, so these are part of the original equations. And now what we are saying is that because we have eliminated A0, right, we have to keep in mind that A0 had its equation, right? That is del I pi I equal to 0.
Yeah, that I understand. I mean, instead of putting the constraint that del dot A is 0, we could have done we could have said that A0 is always 0. That would be the gauge condition.
We could.
Then in that case, I mean, at the level of Rautian, we wouldn't have this constraint, del dot A is 0. It would come only after solving the equations of motion.
Yes, true.
So, I mean, it depends on what kind of gauge condition we are choosing, that we get this constraint or not, del dot A is 0.
I agree. Yeah. So here the gauge condition that you have chosen is a Coulomb gauge. See, for the free Maxwell's theory, eventually it will not really make a difference, right? But in the when you introduce interaction, as we saw, right, that when you introduce, for example, the source term, right, then del dot A equal to 0, the Coulomb gauge is not the same as A0 equal to 0, right? Because you get this A0 is some non-zero value.
Yeah.
So A0 equal to 0 is also a possible gauge choice, right? That's what is called the temporal gauge. And in free Maxwell's theory, temporal gauge and Coulomb gauge are entirely equivalent. But since we will be doing also interacting theory, right, I have introduced it as the Coulomb gauge condition because we don't want to commit to A0 equal to 0. But at this level, we could do either. But you have
so classically,
yes.
So classically in constraint systems, can
Yes.
we like sort of play around with the constraints and the equations of motion obtained from the Lagrangian and mix them up?
Yeah, you can mix them up, certainly, right? So the point is that ultimately what we are saying is that this system, right? So we have gotten some system here, right? Think of this as a Hamiltonian, that these equations of motion together with these constraints is exactly equivalent to the original Maxwell's equation. Because you remember what I said initially, that the way you will quantize Maxwell's theory is that we will first analyze the classical equations to bring it into the form that will be equivalent to the original set of equations, and then we will quantize it, right? So far, you have not done any quantization, right? All you are claiming is that this Rautian, the equations of motion that we derive from this Rautian, together with these conditions, is equivalent to the original set of equations. Is that clear, or there is some still confusion?
Yeah, it's clear.
Yeah, so we are simply saying that the Coulomb gauge condition, right? Because it sets A0 equal to 0, it's as if we have this Rautian, okay, with the understanding that A0, original A0 is 0, okay, together with these conditions, right? This has the same exactly the same dynamics as Maxwell's theory. Okay, are there other questions? Okay. So from now on, we are going to treat Maxwell's system in this way, right? That it's described by this Rautian together with these two conditions. And now, because the Rautian is the same as the Hamiltonian, the equations that we see here are the same as the Hamilton's equation. We can introduce Poisson brackets. Okay, so we think of A and pi as the conjugate variables. Okay. And of course, A Poisson bracket is 0, pi Poisson bracket is 0. And using these, we can write the equations of motion in the standard Hamiltonian form. Namely, del I del t is the Poisson bracket of AI with Rautian, and del pi I del t is the Poisson bracket of pi I with the Rautian. Okay, this is the standard Hamilton's equation. Okay. And of course, we still have to remember that besides this, okay, we have to impose this. We will treat this as constants. Okay. And it's not hard to see that these constants, okay, in this formalism, okay, in this formulation, these constants in fact can be treated as second-class constants. Okay, we'll see this more explicitly in the momentum space. And we have seen that in the Dirac's formalism, if once the constants are second class, okay, there is a standard procedure for eliminating them. And that's the procedure we are going to follow. Okay, eliminate these constants altogether. Okay, are there questions? Okay, so now we are going to proceed more or less in the same way that we did for scalar field theory. So we'll introduce the Fourier transform variables. Okay, so A tilde I is the Fourier transform of AI at fixed time. Similarly, pi tilde I is the Fourier transform of pi I at fixed time. And now we are going to introduce a basis of vectors. Okay, so we introduce two vectors, epsilon A, okay, where A is 1 and 2. Okay. These are defined to be orthogonal to the momentum vector P. Okay. So the idea is that we are trying to going to decompose this three-dimensional vector AI, okay, and pi I in this basis. Okay. So these are two of the three basis vectors. For a three-dimensional vector, we need three basis vectors. So two of the basis vectors we choose to be orthogonal to P. And we just impose this condition. This is not necessary, but this will be convenient. That the basis vector epsilon A that we will choose for minus P is the same as the basis vector epsilon A for P. Okay, because if this is orthogonal to P, then of course it is also orthogonal to minus P. And we just make them to be equal. Okay. So the other basis vector will take to be basically the unit vector along P. Okay, that we'll see in a few minutes. So once we have defined these basis vectors, okay, now we define A tilde I as a component of A along the basis vector epsilon A. So it's basically the inner product between epsilon A and A tilde. Similarly, pi tilde I is the component of pi tilde along this basis vector epsilon A. And then we'll also define the A parallel and pi parallel, or A tilde parallel and pi tilde parallel. These are the components of the basis vector along the unit vector along P. Okay, with this additional factor of I, okay, this is just to ensure that this satisfies the same reality property as the normal Fourier transform variables. Okay. So for example, with this I, okay, this satisfies when you take the complex conjugate, okay, that's the same as changing the argument from P to minus P. Okay, so for this I is needed because as you change the argument from P to minus P, this changes sign and this complex conjugation compensates for this. So to summarize, these are the components of A tilde along this basis vectors epsilon A. This is up to this factor of I. This is the component of A tilde along the unit vector along P. And similarly for pi tildes. Are there questions? So using this, we can now write the expression for this vector A, because all we are saying is that we have this vector A or vector A tilde. Okay. We can express this as a linear combination of the basis vectors, okay, with the coefficient of the linear combination given by the component along the basis vectors. Okay. So you sum over A equal to 1 to 2, that's A tilde A times epsilon A. Okay. And then the other basis vector is unit vector along P. And the corresponding component is minus I A tilde parallel, right? Because you take this I to minus I to this side, it becomes minus I times A tilde parallel. And similarly, pi tilde J is given in terms of pi tilde A times epsilon A and pi tilde parallel times the unit vector along P. And so idea now is that instead of using A tilde J and pi tilde J as independent variables, okay, we are going to use A tilde A, okay, this is two of them, and A tilde parallel as independent variables. Okay, and similarly pi tilde A and pi tilde parallel. So we'll now express the Rauthian back in terms of these variables. And it's a simple exercise to check that the Rauthian, the original Rauthian, which was given in, this is the momentum space expression for the original Rauthian. If you look at this expression over here, and if you convert these to the momentum space variables, right, the Fourier transform variables, the original Rauthian takes this form. Okay, this is 1/4 Fij Fij. You can recognize that's the half B square term. So this one, okay, once we express pi in terms of, okay, pi tilde and pi tilde parallel, okay, takes this form, sum over A equal to 1 to 2 pi tilde, and then pi tilde parallel square. Okay, because this basically just is a change of basis, right? This here is a sum of 3 squares, you still get a sum of 3 squares. Here, however, it's somewhat different because you can easily see that if you take the component of A tilde along P itself, right? When A tilde is proportional to Pi, Okay, and that's what this A tilde parallel coefficient is. Then this term just vanishes, which is a reflection of the fact that the magnetic field vanishes if the vector potential happens to be a total gradient, right? Because it's curl of a vector potential. So the term where A tilde is proportional to P tilde, that means that term that involves A tilde parallel, in fact, drops out of this. So what you get with some little work, one can show that this combination over here just gives the sum over the transverse components of A tilde, namely sum over A equal to 1 to 2, A tilde T minus P, A tilde T. Are there questions? So this is a Rauthian, and you have to also translate the constants, right? Constants, let me remind you again, were these two, right? Which you now think of, which you are regarding as constant now. And those just become pi parallel equal to 0 and A parallel equal to 0, or pi tilde parallel and A tilde parallel equal to 0. So now the content of Maxwell's theory is this Rauthian with these additional constants that you have to impose. Are there questions? Okay. So now it's easy to see that if we look at the Poisson bracket, okay, these are the Poisson bracket between A and pi, AI pi j was delta I j delta q bar minus r prime. This you can translate easily to A tilde I pi tilde j Poisson bracket, because all you have to do is just invert this to write A tilde I as the inverse Fourier transform of AI, and pi tilde I is the inverse Fourier transform of pi I, and just calculate the Poisson bracket between A tilde I and pi tilde j. And you will find, okay, this manipulation is similar to what we had in Klein-Gordon theory, that A tilde I pi tilde j Poisson bracket is given by this structure here, delta ij times delta q p plus p prime. And now given this, okay, we can calculate the Poisson brackets between the A tilde is and A tilde parallel, pi tilde parallel, etc. Okay, because all you have to do is that we will use these definitions of A tilde, pi tilde, A tilde parallel and pi tilde parallel in terms of A tilde and pi tilde. So once you do that, you can easily calculate the Poisson brackets between various quantities on the left hand side of these equations. And in particular, this is what one finds. Okay, that A tilde A with pi tilde B gives to delta AB times delta Q P plus P prime. A tilde parallel, pi tilde parallel gives to delta Q P plus P prime. So these are conjugate variables. These are conjugate variables. And then A tilde A with pi tilde parallel gives to 0. A tilde parallel with pi tilde B gives to 0. And of course, all the A tilde and pi tilde Poisson brackets vanish. Okay, and this is irrespective of whether you take the A component or the parallel component. Okay, all Poisson brackets vanish. So this is something you can easily verify using these equations. Okay, are there questions? And now let's see what these constants give us. So first of all, we can see that these constants are conjugate variables to each other, right? Because A tilde parallel and pi tilde parallel are conjugate. This clearly shows that in this formulation, these can be regarded as second class constants, right? Because A tilde pi tilde parallel Poisson bracket is just proportional to delta cube of P minus P prime, which is the identity matrix, right? So remember the definition of a second class constant, that if you form the full matrix involving the Poisson brackets of constants with themselves, then the matrix will be invertible. Here it's obviously invertible because this is like the identity matrix, right? It's like A tilde pi tilde gives to identity, and of course A tilde gives to 0, pi tilde gives to 0. So this has this block structure, 0 identity, identity 0, and that obviously is invertible matrix. So we'll impose this constant. These are second class constants, so you can basically explicitly eliminate variables using these constants. And in this case, it's easy to see what is the most convenient choice of variables. So we simply put pi tilde parallel and a tilde parallel to 0 and regard the a tilde a and pi tilde a as independent variables. Is this clear? Are there questions? And now I leave it as an exercise to check that the Dirac brackets that involves a tilde and pi tilde b, these in fact are the same as the Poisson brackets, because the constants have vanishing Poisson brackets with a tilde and pi tilde b. So maybe I should go back and show you the definition of the Dirac bracket, just to make things clear. I think it was somewhere. Lecture 4. Okay, yeah. So here was a definition of the Dirac bracket. Okay. The chi's were the constants, and this M matrix is this Poisson bracket. Okay, the precise structure of M will not be necessary, but look at the definition of the Dirac bracket. So FG Dirac bracket is the same as the FG Poisson bracket, and then there are these corrections. So the corrections involve finding the commutator, the Poisson bracket between the F and the constant. Now, in our case, the constants involve either a tilde parallel or pi tilde parallel. The independent variables with whose Dirac bracket you are trying to calculate involve a tilde a and pi tilde a. So a tilde and pi tilde a, of course, have vanishing Poisson bracket with a tilde parallel and pi tilde parallel. So because of this term in fact is identically 0 when you are trying to calculate the Dirac bracket between a tilde a and pi tilde a, okay, or a tilde a and pi tilde b, or a tilde a and a tilde b, etc. And the Dirac bracket just becomes equal to Poisson bracket. And that's what we have said here. That the Dirac brackets are the same as the Poisson brackets. So is this clear? Are there questions? So then here is the final form before we start into get into quantum mechanics, or quantum field theory. So the final form is that the Rauthian is given by an expression of this kind, involving a tilde and pi tilde a, because we have now set pi tilde parallel and a tilde parallel to 0. So that term in the kinetic, so that kind of part of the kinetic term has gone, right? So this is gone. So Rauthian is given by this, and that the Dirac brackets between a tilde and pi tilde b is the same as the Poisson bracket, namely delta AB times delta Q P plus P prime. A tilde B Dirac bracket is 0, pi tilde B Dirac bracket is 0. Okay, are there questions? Is this clear so far? Okay, so if there are no questions, let me proceed. So here are the same equations. The Rauthian, then a tilde pi tilde b Poisson Dirac bracket, okay, and then a tilde b and pi tilde b Dirac bracket. Okay. And let me emphasize again that so far all we have said is that this system, right? You can call it Rauthian or you can now call it Hamiltonian, okay? Because there is a little difference between Hamiltonian and Rauthian. Okay. That this system, okay, the classical equations of motion, okay, for this system are identical to the classical equations of motion of the Maxwell's theory, okay, in the Coulomb gauge. Okay. So that's the statement. Okay. So we have gotten an equivalent classical system to the original Maxwell's theory, okay, and now we are going to quantize this. Okay. And we are going to quantize this by simply regarding the Rauthian as the Hamiltonian and the Dirac brackets as the commutator bracket divided by I. Okay. So that's the standard procedure for quantizing a classical system. So this is just a rewriting of this equation. So now I have written it as Hamiltonian, the same expression. Okay, but now these have to be thought of as quantum operators. And the instead of the Dirac bracket, I have now replaced it by commutator bracket. So a tilde pi tilde b commutator bracket is of I times delta a b delta q p plus p prime. A tilde b commutator bracket is 0, pi tilde b commutator bracket is 0. And now you would notice that this is identical to a system that contains a pair of zero mass Klein-Gordon fields, one for each A, right? That if you fix your A, then this Hamiltonian and these commutator brackets are identical to what we had for the Klein-Gordon field. The only difference is that for the Klein-Gordon field, we had a p square plus m square. Here we have just p square, which basically is saying that this describes the theory of massless particles, zero mass particles. And not one zero mass particle, but two zero mass particles. Okay, two different types of zero mass particles because of this index A.
Sir?
Yes, go ahead, please.
Sir, in the starting where you introduce this epsilon basis vector,
Yes.
yeah, there you have taken this index A, right?
Index A, yes.
So, and it runs from 1 to 2. So I just missed that part. That why there are two basis vectors?
Oh, because we are trying to decompose a three-dimensional vector, right? Okay. A tilde I was AI was a three-dimensional vector, or A tilde I was a three-dimensional vector because I runs from 1 to 3. Okay. And we introduced three basis vectors to expand that A tilde. Okay. Two of them are transverse to the momentum, right? In three dimension, if you have one momentum, then there are two independent vectors that are transverse to it, right? So those are the epsilon A's. Okay. And the third basis vector I took to be the unit vector along P.
Okay.
Okay, so this number 2 comes because you are working in three space dimensions, right? In higher spatial dimensions, you will have more basis vectors of this kind.
Okay, thanks.
Any other question? Okay. So now we are going to quantize it. Okay, so we have already quantized it. Okay. But now we are going to proceed exactly as in Klein-Gordon theory. Okay. So we'll introduce our annihilation and creation operators. Okay. But this time, one annihilation operator for every B. It means that there should be two different kinds of annihilation operators, which are denoted by AB, okay, labeled by T and P. Okay. This is exactly the same as what we had for Klein-Gordon theory. There it was phi tilde and pi tilde. Okay. Instead of that, here you have an A tilde B and pi tilde B. Okay. And this is the Hermitian conjugate. So it's basically the Hermitian conjugate of the first equation, okay, with the understanding that the Hermitian conjugate of A tilde B Tp is A tilde B T minus P. Okay. And that basically is follows from the fact that in the Fourier transform, right, there is an exponent of e to the I P dot R. Right? So when you complex conjugate, that P gets changed to minus P. Okay. This we had seen also in the case of Klein-Gordon field. Okay. So these are exactly the same equations. And the definition of EP is just itself mod P. Right? M is 0. And then it follows from these commutation relations that AB-AC dagger commutation relation gives you delta BC times delta QP minus P prime. These are like two different Klein-Gordon field operators, Klein-Gordon annihilation and creation operators. Okay. And AA commutator is 0, and similarly AB dagger, AC dagger commutator is 0. Okay. And the Hamiltonian, okay, this one, when we express in terms of these creation annihilation operators, they take the standard form. Okay, again, this is the same as what we had for Klein-Gordon theory. Okay. There you had EP times A dagger P, A dagger P. Okay. Now you have a sum over B because there are two different kinds of creation and annihilation operators. Okay. But of course, EP is the same for both, right? Because as you can see, this one doesn't depend on P. It is both for both of these, it's just P squared. And given this form, the Hamiltonian, one can calculate the commutator between Hamiltonian and A, which is given here, and between Hamiltonian and A dagger, which is given here. Okay, so are there questions or comments? Okay, so if not, let me proceed. So here is the Hamiltonian again with the appropriate commutation relations. So in the Heisenberg picture, we will now build the basis of states, okay, and they are constructed at t equal to 0 as usual. Okay. So you define AB of P as AB at time t equal to 0. Similarly, AB at P dagger is AB dagger at time t equal to 0. And then you define the vacuum state by saying that the annihilation operators annihilate the vacuum. Okay, so AB of P acting on the vacuum gives you 0. Okay. And this has to hold for every P and also for B equal to 1 and 2. Given this vacuum, we can create a single particle state by acting with AB dagger. Okay. And the multi-particle states, of course, will involve acting with AB dagger many times, as before. But the single particle states, these states carry energy EP. So again, this is saying that there are two different kinds of single particle states. Both carry the same energy EP for a given P. Now, there is something that we have learned in the Klein-Gordon theory, is that when you consider the conserved momentum, Pi, and act on this state, then you get an eigenvalue Pi, small pi, which shows that the small p actually describes the momentum of the state. And the same statement is true here also. But like in the case of Klein-Gordon theory, to see that this p label, right, actually refers to the momentum of the particle, we have to first construct the momentum of particle using the Northrop procedure, which is more or less straightforward. And then you can verify that indeed this Pi is the momentum that the particle carries. So once you have identified the energy EP as the energy and P as the momentum, then you see that the relation that EP is mod P basically tells us that these are describing massless particles. So what this is saying then is that there are two different kinds of massless particles in this theory. And these two different massless particles are called photons. They are called, both are called photons, and the index B basically describes the photon polarization. So if you think of B, if you remember what B labels, right, these labels two vectors that are orthogonal to the direction of motion of the direction of the momentum. And this is exactly the two polarizations of the electromagnetic wave, right? If electromagnetic wave is propagating in certain directions, we know from classical electrodynamics that there are two independent polarizations. What we are saying here is the quantum version of that, that the photon exists in two different states, and those two different states correspond to two different polarizations of the electromagnetic wave that you are familiar with. Are there questions? And from this interpretation, it's also clear that if you rotate, say, along the axis of motion of the photon, then that rotation basically mixes these two different kinds of polarizations, right? It transforms one polarization to another polarization. Okay, so if there are no other questions, I'll proceed. So these states that we have constructed are what we can call linearly polarized photons, because they are analog to the linearly polarized electromagnetic waves. But we can also, of course, consider any linear combination of these, right? So in particular, we can consider linear combinations of the form A1P dagger plus or minus I times A2P dagger on the vacuum state. Okay. These are also single particle states, just linear combinations of these. And these can be said to describe circularly polarized photons, because the corresponding electromagnetic waves are circularly polarized electromagnetic waves. And now one can show, okay, this is something that I'm not going to discuss, but one can show that these states, in fact, form eigenstates of the component of angular momentum along the photon momentum p. Okay? And the eigenvalues that they represent are eigenvalues plus or minus 1. Okay? And this is saying that in some sense, the photon represents a spin 1 particle. Okay? For Dirac particles, okay, that we'll see next, similar calculations will tell us that the angular momentum eigenvalues are plus or minus half. For photons, on the other hand, okay, the angular momentum eigenvalues are plus minus 1. If you had done this for Klein-Gordon field, right? Take a massless Klein-Gordon field and okay, and say it's moving along certain directions. Okay? And if you apply the angular momentum operator, this component of the angular momentum along P on the Klein-Gordon field, you will find that the result is 0. Okay, so that is basically a reflection of the fact that the Klein-Gordon field represents a spin 0 particle. Okay. But to see this, right, what one needs to do is to first construct these Noethern currents, J mu nu, and then take this particular combination. Okay, what this combination is doing is basically this is projecting the angular momentum along the direction of motion of the photon. Right, Pi is the direction of motion of the photon. Okay. Epsilon ijk jjk is really the angular momentum vector. Okay. And so this is the inner product between the photon momentum and the angular momentum vector, which basically is saying that it's projecting the angular momentum along the direction of motion of the photon. Okay. So when you calculate this operator, okay, and then apply it on these states, okay, you can verify that these states carry eigenvalues plus or minus 1 under this operator. Are there questions?
So why did you say that this is an indication of photon being spin 1?
Because the angular momentum component along certain direction taking eigenvalues plus minus 1, right, is what we expect of a spin 1 particle, right?
Yeah, but I mean, we are taking a specific direction, right?
Yes, we have taken a specific direction, right? But whichever direction you take, right, a spin J particle will have all angular momentum components between J and minus J, right?
Yeah.
So here we are getting only 2 values, plus or minus 1, right? So in this sense, you can say, how can it be spin 1? Because spin 1 should also have allowed the 0 component, right?
Yeah.
Okay. And this is very specific to massless particles. Okay. That when you look at the representation of the Lorentz group, okay, you find out for massive particles, right, the particles have to form representation of the corresponding SO3 rotation group. Okay. Because you can always go to the rest frame of the particle. Okay. In which case, rotation group, under rotation, the particle at rest remains particle at rest. Okay. And you can classify the particles by their usual angular momentum quantum numbers. And indeed there, if you have a spin 1 massive particle, right, and if you fix any direction, you should get all 3 states, both components plus minus 1 as well as 0. But for photons, because they are massless particles, there is no sense of going to the rest frame. But you can look at the angular momentum components along the direction of motion of the photon. Okay, you can decompose in along the direction of the motion of the photon, and a particular representation, okay, involves giving components plus minus 1. Okay, in fact, for massless particles, right, you have representations where it can take plus minus n for any integer or half integer n, right? Just as from the representation theory of Lorentz group, you can show that you can get any representation that takes a value plus minus n with n integer or half integer. And those we normally describe as massless spin n particles. Okay, so
is there a possibility of any spin massless particle?
As far as the if we just look at the representation of the Lorentz group, then there is such a possibility, right? Just representation theory of the Lorentz group, doesn't exclude such particles.
And you said if we would have done this in the Klein-Gordon case, we would have gotten what?
0. Suppose you have taken a massless Klein-Gordon field.
Yeah.
Right. You construct the angular momentum generator there.
Yeah.
And you calculate this combination and apply it on the on a single particle state. You will find 0 eigenvalue.
And on a massive field?
On a massive field, if you go to a rest frame, right, then again you will get 0. Yeah, in fact, you can even for the massive field, I think you will get 0 in this case. So basically, what this is doing, J contains both an orbital part and the spin part, right?
Yeah.
What this combination is doing is that it's basically removing the orbital part, picking up only the spin part. And for Klein-Gordon field, we know that the spin part is 0, right? There is no spin part. You remember, let me remind you the definition of the spin, that sigma matrix that we had. Let me see if I can locate it. Do it somewhere here. Later. Yeah, Lorentz invariance of the Klein-Gordon action. Yeah. See here, we found only this x nu t mu tau minus x tau t mu nu term, right?
Yeah.
So this part you can easily verify that when you take that combination epsilon ijk pj times jjk, it gives you 0. Okay. So let me. So but then we introduce this S mu nu matrix, right? This is for a more general class of fields. Okay. These are the ones which will contribute to that particular combination. And the Klein-Gordon field simply doesn't have this. Okay, that's why it gives you 0 identically. So this final form, let me show the final form of J that you get here. Yeah. So this part, right? This is the whole form. This is the m mu nu tau, right? Whose integral gives you the m0 nu tau integral gives you the j nu tau. So here, this is the part that will contribute to this Pij epsilon ijk Pijjk combination. Okay, this part gives you 0, and because Klein-Gordon field doesn't have this part, it gives you identically 0.
Okay.
Okay. Any other question? Okay, so this is I think what I have already said. That if we take this combination, right, then we will find the eigenvalues plus minus 1. Okay, and this is a reflection of the fact that the photons have spin plus minus 1.
One thing.
Yes.
Yeah, just to add, like when we considered something like in the Klein-Gordon case, phi going to some replacing phi by some chi plus lambda chi square or something.
Yeah.
If we were to do that here, replacing a mu all the 4 fields by some appropriate a prime plus lambda a prime square.
Okay.
Mu, all 4 fields. So will we and in the primed picture, the particles, will they have some spin attribute?
Yeah, they will have spin attribute. It's just the if the change of variable that you have done, right, is not manifestly Lorentz covariant.
Yeah.
Then the Lorentz transformation properties of the new fields will be very complicated, but nevertheless they are there. Right, and using that you can certainly attribute spin.
But not necessarily some plus minus 1 or something.
No, it will be same plus minus 1. Because you are not taking the theory, right? You are just rewriting this.
Yeah.
But the actual expression for the generators in terms of the fields will become more complicated.
But the eigenvalues will come out to be the same, you're saying?
Yeah, the eigenvalues will come out to be the same because these are physical quantities, right?
Yeah, but we don't have a physical interpretation of this substitution, right? In the sense that if we have 5 particles in nature, we do not necessarily have chi particles where phi is equal to chi plus chi square.
No, we have. They are the same particles.
What?
The phi particle and chi particle, right? The physical phi and chi particles are the same. Right? Because the point is that this is what I emphasize, that you see the phi particle, right? In the full quantum theory, the phi particle is the pole in the Green's function of phi, right? In momentum space, Green's function, if you calculate the phi, right?
That
The
is
pole,
just the mass of that.
yeah, this is the mass of that, right? But that's a reflection of how to create the phi particle, right?
Yeah.
Similarly, for the chi particle, it will be pole at the same place, because
Okay.
So this is one, okay, this is one reflection, that phi and chi particles are the same. Okay. Then if you look at the scattering matrix, right, you will construct the in states, right? And as you have emphasized, the in states could be constructed by phi, but it could be constructed also by any other combination, right? Phi plus phi square is as good a combination to create an in state as phi itself, right? The only thing that is going to change is that Z factor, okay, will change. But otherwise, it's not necessary that you have to use the elementary fields to create in states and out states. So this is the reason why whether you write the theory in terms of phi or chi, it doesn't matter at the level of the S matrix elements. Green's functions will be different, right? Green's functions of phi are different from the Green's functions of chi's. But S matrix or the masses of physical particles, those are not going to be affected by this change of variables.
So suppose in some weird transformation, I find out that two chi particles going into two chi particles at some angles is the matrix is zero.
The same will be
Like
true
the
for phi.
matrix element. What?
Yeah, the same will be true for phi particles. If you work with chi
Even though that might not be manifest in the Green's function notation.
Yes, exactly.
All right.
In fact, I mean, I think I don't know if I have given this. Maybe I haven't set it up as a problem. That if you start with a free field, right?
Start with what?
A free field theory, free Clark-Gordon field theory, right? Then the S matrix is trivial, right? All the non-trivial S matrix elements are zero. So if you write now this free field theory in terms of chi, by making this change of variable, right? In terms of chi, the Green's functions are very complicated.
Yeah.
But nevertheless, when you actually calculate the S matrix, you will find that all the S matrix elements are zero, except the forward scattering ones.
Yeah.
Right. So that's one example where you see that this change of variable affects the Green's function in a non-trivial way, but not the S matrix.
I see. Okay.
Okay. Any other question?
Actually, even the mass will come out to be complicated.
Mass will come out to be complicated.
Yeah, in the sense that in free theory, the mass of the phi particle is just m.
Yes.
In the chi theory, there will be some m and lambda combination of MP.
Well, I think no. I mean, if you do the calculation, you will find that they are also the same.
I mean, should they additional terms cancel out or something?
Yeah, they will all cancel out.
Okay.
Right? They may affect the wave function Ramanson factor Z, but not M. Because the location of the pole is a physical attribute of the particle, right?
Yeah.
So that is not going to change.
All right.
Okay, any other question? Okay, so let me proceed.
Sir?
Yes, go ahead, please.
Sir, just about this discussion just you had.
Yeah.
So any field ray definition would be fine if it doesn't spoil the symmetries of Lagrangian. and doesn't affect the physical observable lights like S matrix and the mass of the physical mass of the particle.
Yes, this is the other way, that any field redefinition, right, cannot destroy the symmetries of the Lagrangian, nor can it change the S matrix or the physical masses of the particles.
Okay, any redefinition.
Well, unless the redefinition is singular, right? You don't want to make phi equal to 1 over chi or something.
Okay.
As long as the redefinition is non-singular, this is true.
Okay, so we don't have to worry about that. It respect the Lagrangian symmetry at the first place.
No, because it will not, the symmetries will remain, right? See, if the original Lagrangian had a symmetry acting on phi, right?
Yes.
Just by rewriting phi in terms of some chi, you cannot destroy the symmetry, right? It's just in terms of chi, the symmetry will look much more complicated.
Okay.
Right? But you can look at the transformation of phi and from that work out how the chi's will transform, right? Because chi's are after all functions of phi, right?
Okay, the definitions of transformation will change.
Yeah, definition of the transformation will change, but the transformation will still remain symmetry of the Lagrangian or action.
Yeah, and they will describe the same physical transformations in
Exactly.
the terms of phi or chi.
Exactly.
Okay.
Any other question? I think Harshit was trying to ask something, but probably his phone was not working properly. Anyway, we'll come back afterwards. Okay, so now we are going to try to calculate the Feynman propagator. Okay, I'll start the discussion today. We'll see how far we can go today. Okay. So what is the goal? We'll calculate this d mu nu xx prime, which is the vacuum expectation value of the time ordered product of two gauge fields. Okay, a mu nu. And to do this calculation, we will proceed exactly as in the case of Klein-Gordon theorem. Namely, we will first write this d mu nu in terms of its Fourier transform. And it will be understood that when I say that you calculate the time ordered product of mu nu, of course, not all components of mu and nu are quantum variables, right? So the ones which you have set to 0 will still be regarded as 0. Okay. So by a tilde mu tp, I basically mean that a tilde 0 is 0, pi a tilde I is 0, right? Because that's the a tilde part, a tilde parallel. Only thing that is a genuine quantum field is epsilon IB times a tilde I. Okay, and that's what we had called a tilde B. These can be expressed in terms of the creation and annihilation operators AB and AB dagger. Okay. So the strategy that will be following is that we will first use these relations to express a tilde mu and a tilde nu, okay, which are appearing here, in terms of a tilde B, right? Because the only non-zero components are a tilde B here. And then these in turn will express in terms of AB and AB dagger. And then finally we'll evaluate the matrix element. Okay, we'll get some matrix element involving A's and A daggers, and that we can evaluate by the standard procedure. So that's the strategy that will be following. Okay. Are there questions, comments? Okay, if not, let me proceed. So again, I have said this here, the a tilde mu satisfies these conditions. Okay, this is the definition of what we mean by a tilde mu. Okay. So now with this, let's introduce this following contravariant 4 vectors. Okay, so now you are trying to describe a basis of 4 vectors in the 4-dimensional space. Earlier you had introduced this in the 3-dimensional space. Okay. So n will be a contravariant vector whose first component, namely 0th component is 1, everything else is 0. P bar is basically a 4 vector, but whose 0th component is 0. The other 3 components are the momentum P. And eta bar B, for B equal to 1 and 2, are again 4 vectors, but again the zeroth component is 0. And the spatial components are given by epsilon b. And you can easily see that this forms a linearly independent basis states in 4 dimensions, right? So 1 here, 2, and then 2 of them here. That's the 4 independent basis vectors. So then these conditions that we have here can be written as n dot a tilde is 0, p bar dot a tilde is 0, and eta bar b dot a tilde as a tilde b. Okay, so these are exactly the same conditions that we had seen earlier, except that we have rewritten as dot products in the 4-dimensional space. Okay, earlier, for example, we had defined a tilde b as a dot product in the 3-dimensional space, epsilon b vector with the spatial components of a tilde. Okay, now we are just rewriting this as a dot product in 4 dimensions. Okay, is this clear so far? Okay, so now we make a claim that eta mu nu can be expressed in this form. This relation of this kind you are probably familiar with in 3 dimensions, right? In the usual Euclidean space, okay, when n-dimensional Euclidean space. Okay. This is basically a decomposition of the identity matrix in a complete set of basis states. This is the analog of that in Lorentzian version. Anyway, this is both sides are completely well defined, right? 2 index, this is a 4 by 4 matrix on the left hand side, 4 by 4 matrix on the right hand side, and the claim is that these two are equal. And the easiest way to check this, okay, is to look at the following observation: that imagine that you have 2 4 by 4 matrices A and B, okay, and you want to prove that the 2 matrices are equal. Then it is enough to show that if we take the difference A mu nu minus B mu nu and contract with some vector V, if this is 0 for 4 linearly independent 4 vectors, then this matrix is identically 0. And the reason for that is because any 4 vector can be expressed as a linear combination of these 4 different 4 vectors, right? So if this is true for all of these 4 linearly independent 4 vectors, then this is true for any vector. And that basically means that this matrix must be 0, right? Because the matrix, 4 by 4 matrix contracted with any vector is 0, can only happen if the matrix itself is 0. So this gives you a way to check this, because we already have introduced 4 linearly independent 4 vectors, eta n p bar, eta bar 1 and eta bar 2. So all you have to check is that eta mu nu contracted with n is 0, not 0, eta mu nu contracted with n is the same as this matrix contracted with n. So let's check that. So eta mu nu n nu will give you n mu on the left hand side. And when you contract with n nu here, okay, the n square gives you minus 1. That gives you back n mu. This is 0 because n dot p bar is 0. You see the definition, n dot p bar is 0. Similarly, n dot eta bar is 0. So this relation obviously holds when both sides are contracted with n nu. And the same thing can be checked for either p bar nu or eta bar nu. Okay, so this I'll leave as an exercise to check this. And because of this, we know that this relation is true. And you are now going to make use of this relation and these to express a tilde mu in terms of the a tilde b's. Okay. Other questions? Okay. So here I have listed the relations again. Okay. This is the expression for eta mu nu in terms of this decomposition. Okay. And these are the conditions for a tilde. Okay. So using this, we can write a tilde mu. Okay. Of course, this is the same as eta mu nu a tilde nu. Okay. For eta mu nu, I substitute this. Okay. And now you see that the first term gives you 0 because it gives you an n dot a tilde. Right, n dot a tilde is 0. The second term gives you 0 because it gives you p bar dot a tilde. So the only term that remains is this one. So you get sum over b equal to 1 to 2 eta bar b mu times a tilde b. And that's exactly what we had expected, because a tilde b's are the only non-zero components of a tilde. And this is basically saying that a tilde mu can be expressed in terms of a tilde b in this way. And now we are going to substitute this in the expression for the propagator, the Feynman propagator of the photon. Okay, are there questions? Okay, so let's then do this. So d mu nu xx prime is given by this integral. Okay, this was the original expression for d mu nu xx prime, and now I'm going to rewrite a tilde mu in terms of a tilde b's using this. So that gave you this double sum over b and c, okay, or theta bar b and eta bar c. Then this 2-point function. And now what we are going to do is that in this 2-point function, we are going to express a tilde b in terms of ab and ab t minus p dagger. Then you are going to use this commutation relation, right? The commutator of the AB with the Hamiltonian is minus CP times AB. This is what we had seen earlier. And similarly for AB dagger. So using this, we can solve for time dependence of AB and AB dagger, right? Because we have an equation that relates the time derivative of AB to this commutator. So by integrating that, we get the time dependence of AB and AB dagger. Okay, this is exactly the same as for the Klein-Gordon fields. So you get ABTP as ABP of e to the minus IEPT, ABTP minus P dagger is this. So using this, we replace this A tilde BTP in terms of ABP, and similarly A tilde C T prime P prime in terms of AC dagger. Okay, AC and AC dagger. And finally, we have to use this relation. Okay, again, this is the same as that we did in the Klein-Gordon theory. Okay, that the only non-zero matrix element for the 2-point function is one where the first one is A, second one is A dagger, because other terms are all zero. Okay, if this was A dagger, for example, it will annihilate things on the left. If this was A, it will annihilate things on the right. So this is the only possible combination, and this combination gives you delta BC times delta QP plus P prime. Okay, that's from the commutation relation between AB and AC. So using this, we can basically simplify this. Okay. Substitute for A tilde B and A tilde C in terms of AB, AB dagger and AC, AC dagger, okay, and then just carry out the manipulation. Are there questions? Okay. So at the end, okay, this is what we get. Okay, this is a straightforward exercise. This is the Heaviside function. This Heaviside function comes because of the definition of time ordering. Right? Time ordering tells us that when t is larger than t prime, it's one order. When t is less than t prime, it's another order. That's why these Heaviside functions come. So this is just algebra. We write d mu nu in this form. So you get these Heaviside functions. And then here you see that here it was p and p prime, right? But because of this delta q p plus p prime that comes here, p prime got set equal to minus p. So A tilde B and A tilde C, okay, even though we had to begin with eta B and eta C, okay, and this was P and this was P prime, okay, we eventually got eta B of P. This should have been eta B, eta C of minus P prime. Sorry, eta C of P prime, okay, where P prime is minus P. Okay. But eta, of course, we have chosen so that at minus P and P, it takes the same value. Remember, I had said that the epsilon B will be chosen. So epsilon B of minus P is the same as epsilon B of P. Okay, it's a convention, but it's a useful convention. Okay, using that, we can write this as eta bar of P, and the C become B because of this delta BC. Okay, so eventually we get eta bar B, eta bar B. And the reason that I have taken care to write it this way is because now, using this relation, I can rewrite this in terms of eta mu nu, n mu n nu, and p bar mu p bar. So this one can be replaced by this. So you see that in this form, the precise choice of the basis vectors are not important anymore, right? Because this has gotten eliminated, right? Now everything is a well-defined vector. Earlier, you see this eta bar b, I didn't give the explicit form, right? I said that we have to choose this to be orthonormal to the vector p. But now there is no choice involved. Okay, you have already performed this sum and you have to rewritten this in this form. Okay. So using this, we can replace this by this. Okay. And as far as this part is concerned, okay, we follow exactly the same trick as in the case of Klein-Gordon field, okay, to write it in a more coherent for notation where you have instead of d cube p, you have integral d4 p. Okay. So this is what you have said here, that using this we can write d mu nu xx prime in this form, okay, as d4p over 2 pi to the 4 to the ip dot x d tilde mu nu. Okay, d tilde mu nu, this part is what we get from here. Okay. The rest is just what we had for Klein-Gordon field. Okay. So the idea is that if you take this, okay, and then do the p naught integral, okay, by Gauss's residue theorem, okay, you will basically reproduce this structure over here, okay, just as in the case of Klein-Gordon field theory. The only difference here is that there is a non-zero mass term. Here the mass is 0. Okay, are there questions, comments? Okay, so this is d tilde mu nu. And so what we are going to do next time is that we will describe that given this propagator, okay, so this plays the role of delta f for the Feynman propagator in the Klein-Gordon theory. And now by following exactly the same procedure as in the case of Klein-Gordon theory, using this propagator, we can calculate any arbitrary Green's function that we can ask for. Okay. So any arbitrary Green's function involving the gauge fields and possibly the derivatives, okay, can be expressed in terms of d tilde mu nu by simply following the same Feynman rules as in the case of Klein-Gordon theory. Okay. Wherever you are using Feynman propagators for the Klein-Gordon field, right, delta f, we have to replace it by the corresponding propagator d mu nu. And we will see examples of this in the next lecture. Are there questions? Again, I think probably Harshit is trying to ask something, but somehow it's not coming through. Yeah, if it doesn't come through, maybe we'll discuss it tomorrow. Okay, hopefully the connection will be better.
So these delta AB and delta BC are a signature that we cannot just shift polarization, right?
Well, it's a signature that the two different polarizations are orthonormal to each other, right? They are really independent fields.
Yeah, so in scattering cross section later on, we won't get cross terms, right?
No, when you have multiple fields, right? We can certainly get cross terms.
So a photon may change its polarization while scattering.
Yes, it can.
Okay.
Right? It can change its polarization while scattering, depending on, of course, the precise form of the scattering. Because there is no reason why the interaction terms will also we have exactly the same delta BC.
The symmetry of the Hamiltonian that, or the Lagrangian that, since these are two independent, these are like two independent Klein-Gordon field, we can take one into the another by rotation, right?
Yeah, in this case, we can take one into the other by rotation.
Yeah, somewhat like what you gave in the midsem problem.
Yes, that's right. That was some
Now,
internal rotation, but yeah, it's like that.
yeah, so that also has a conserved quantity.
Yes.
Isn't that what corresponds to the polarization of the...
True. But the point is that in scattering, angular momentum can be transferred, right? Total angular momentum is conserved, of course. But there's nothing which prevents you from transferring angular momentum to another particle.
Okay.
Right? See, even in that exam problem, right, we had these two fields, phi1 and phi2. It's certainly possible to write down interactions where a phi1 changes to phi2. But of course, something else has to happen, right? It cannot be just a phi1 changing to phi2, because that will be inconsistent with the conservation laws. But you can certainly have interactions where this can happen.
We can add terms like phi1 phi2 square plus phi1 square phi2.
No, I think that will not be invariant under the symmetry, right? But you can imagine another particle, chi, coming in, right? Chi1 and chi2, which also rotates under this symmetry.
All right.
And then chi1 and phi2 could collide and become chi2 and phi1.
Okay. Yeah.
Right? So here, for example, once you introduce electrons, right? Electrons also carry spin, and the photon can exchange spin with the electron.
All right.
Sir, hello.
Yes, go ahead, please.
Can we have poles on imaginary axis in the propagator?
Yes, we could. That will mean that the particle is unstable.
Yeah. So I mean, I was thinking if we could have massless bound states.
In principle, you can, but bound states are not necessarily poles on the imaginary axis, right? Bound states are still poles on the real axis. It's the unstable bound states which will be poles on the imaginary axis or in the complex plane.
Okay.
Right. So a massless bound state. Okay. I mean, at the level that you are considering, right? Nothing prevents us from having massless bound states, but there are some theorems, right, by Weinberg and Witten, which basically rules it out, right? I mean, these questions came up because people tried to see, for example, we could regard the photons as bound state or the graviton as bound state of two particles, right? And this general theorem basically ruled out such possibilities. But at the level that we have studied so far, there is nothing which prevents us from having that.
On what grounds do people rule out such things? Like,
well, it's called Weinberg-Witten theorem. So you have to basically look at the detailed analysis of the theorem, right? What the assumptions are and so on. But basically, it tries to rule out compositeness of photons and gravitons, right? That if you start with a local quantum field theory without gravitons, can you get graviton as a composite object, for example? Right? Those are the kinds of questions that this theorem addresses.
Also, there is apparently, I'm not sure, but like in flat space, we cannot have a spin greater than some number of particles, stable particles. Some theorems like that.
Yes, that's right. I mean, what the theorem is that you cannot have, again, it's a Weinberg's theorem, that you cannot have interacting theory of massless particles of spin larger than 2.
Okay.
Okay.
So
theory you can write down free field theories, right? But there is a consistent interacting theory of massless particles of spin larger than 2.
Okay.
Again, these are not theorems which are easily seen from what you have studied, right? It requires detailed analysis of quantum field theories to rule out these possibilities.
But the grounds of these theorems are still quantum field theory, right?
Yeah, it's still quantum field theory.
Okay.
Yeah. Maybe another point I can say that, I mean, there is a question of whether the photon mass can get renormalized, right? So one of the arguments why the photon mass cannot get renormalized is this feature that photons have only two polarizations, right? So the photons, you can see, has in the degree of freedom that describes photons, right, has only two fields. Whereas if, let's imagine that the photon got a mass, okay, a massive particle necessarily have 3 degrees of freedom, right? It has because you can go to the rest frame of a massive particle and it has 3 spin states, right? Spin 1, spin 0, and spin minus 1. Okay, not spin, the spin component, 0, 1, and minus 1. Okay. So there is a discontinuity because between describing a massless particle and a massive particle, okay, that you have to actually change the number of fields. It's not enough to change the mass, you have to actually change the number of fields. And that is typically very hard in a quantum field theory, right? You cannot suddenly add a field. Okay, once you have formulated the theory in terms of 2 fields, you cannot just get back a new field. So this is one of the arguments, right, which one can use to show that the photon mass is not renormalized. That in any consistent theory, once you have started with a massless photon with 2 degrees of freedom, it will remain a massless photon with 2 degrees of freedom.
So we could not even have bound states in these theories, which are spin 1. Sorry, yeah, kind of.
Bound states, okay, Maxwell's electrodynamics, of course, is too trivial. But
if we were sort of adding interaction terms in this Maxwell's theory, let's say mu square.
Yeah, so it can have massive bound states in principle.
Although the particles that it describes are massless.
Yes, I mean, a priori, there is no reason why you cannot have massive bound states. Okay, QCD, for example, right, quantum chromodynamics is exactly such a theory. If you ignore the quarks, right, it's a theory of apparently massless particles, right? It's exactly like electrodynamics, except that we have some interaction between these fields. Okay? And it's known that the spectrum, okay, contains massive objects called glue balls. Right? So those are like massive bound states which are gotten out of the massless theories. A theory which starts its life as just massless particles. So that is certainly possible. Okay, I think the next class is probably starting, so I may have to stop. So we'll continue tomorrow. Okay, any other questions you have, we can discuss tomorrow.